So the gradient of Pc at the point A would be 0. So we will this. So we go to next page. We just observe that A is minimizer, local minimizer of this function Pc. Pz is fz yz. Therefore, the gradient of Pc is 0. So 0 is the gradient of Pc at the point A, which is by the chain law plus here the B is YA. Then we have this equality. On the other hand, from the Gz is 0, we also have 0 equal G at AB plus the partial derivative of G which is respect to Y also at AB multiplied this. Now we observe that the determinant is not 0. This determinant, the partial derivative of G at x0, that is at AB, which is respect to Y, is not 0. So the following system of linear equation by Coulomb law. There exists a lambda such that the partial derivative of f which is respect to y at AB plus the transport of lambda, then the derivative of y which is respect to y at AB is 0. Why? Because usually our system of linear equation is ax equal b. If the determinant of A is not 0, then for every b, you have a unique solution for this system of linear equation. But the system of this equation, this system of equation can also be written as minus b transport plus x transport A transport 0. You can also write this equation in this way. So our equation, our system of equation is this, precisely the transport version of the system of linear equation. Here this is our A, no singular metric, determinant not 0. So for any for this vector, this is an 1 by n row vector. We can solve for lambda for this equation. So we can obtain a lambda satisfies this equality. Now we multiplying the solution of this system lambda transport to this equation. We obtained 0 is the transport of lambda, then dzgab plus lambda transport dygab, then y prime a. Multiplying lambda transport to this this equality, to this red border equality, we obtained this equality. Okay. Now then we use this equality for the solving lambda, for the equation we use to solve lambda. We obtain that this is precisely lambda transport dzgab plus the lambda transport dygab is precisely minus, so here is minus minus dyfab and y prime a, right? This part can be replaced by the minus partial derivative of f with respect to y. Using the equation we solve for lambda transport by the Kolmogorov law. Okay, so this means that dyfab y prime a, oh no place to write, sorry. This means that dyfab y prime a is lambda transport dzgab. Moving this term to the left hand side of the equality, we obtained the final equality. So we insert this result, substituting this result to the first equality here, to the equality here. I have a type. This is not z, this is y. Sorry. Here it should be y. By the chain law, this is y. So this part of this equality, we move this to substituting this result into that result, we obtain the 0 is the dzfab plus lambda transport dzgab, right? So this equality and the equality we solve for lambda transport altogether, we will obtain our result. We go to next page, but we need to copy everything to the next page. For the equation for lambda transport here, this equation, we use Kolmogorov law to solve for lambda transport is the dyfab. Okay, so we have dyfab plus lambda transport dygab is 0. This is the equality we obtained using Kolmogorov law. Then we also have the final equality dz, replacing the dy by dz. The final equality is obtained by substituting the lambda transport into the result obtained from taking derivative of gz yz equal to 0. Okay, and then by some simple multiplication, we will obtain the last equality. So we'll copy this equality to the next page, and then we will get our result. That is dzfab plus lambda transport dygab also 0. Okay, we obtained these two equations. Then the gradient of f at AB, that is dZfAB dyfAB. This is minus lambda transport dZgAB. Sorry, here is Z here. Here is Z. The Z okay. So so here is also Z. Then minus lambda transport dYgAB. That is minus lambda transport dZgAB dyGAB, which is minus lambda transport the derivative of G at the point AB. But AB is x0, y0. And sorry, AB together is x0. So this is the conclusion of the theorem. And this proves our result. Finally, we provided the third proof of the Lagrange multiplier theorem. To this purpose, we need the following lemma. Linear algebra. Suppose V1, Vn is some vector in Rn which are linearly independent, and V is a vector in Rn. Then, if H is orthogonal to the subspace spanned by V1, Vn, for every V orthogonal to this subspace, we have H. For any H orthogonal to this subspace, we always have H orthogonal to V. Then V belongs to the span of V1, Vn. Okay, so this is completely a result in linear algebra. The proof is also very easy. Proof. Because V1, Vn are linearly independent, we can extend V1, Vn to be a space to get a base of the space. That is V1, Vn, Vn plus 1, Vm. And we can also assume this base has further properties. The first n vector are given. We could not assume something. But for the later n minus n vector, this is we add into the this group of vector V1, Vn to form a base. But we can choose Vn plus 1, Vm suitably so that they are orthogonal. Okay, that is such that for I and j greater than n, strictly or greater than n plus 1, we have all this Vi orthogonal to the span space of V1, Vn, and also their inner product, their scalar multiplication is delta ij.